So this is part B of 2002 AP exam number 5, and it's the problem about the cone. And in part B, it says find the rate of change of the volume of water in the container with respect to time when H equals 5. So we want the rate of change of volume. And so if you think about that question, basically what it means is we want to know what dV dt is, the derivative of volume with respect to time at the instant in time when there are 5 centimeters of water left in the cone. So when H equals 5 centimeters. So what is this? That's what we want to know. If we want to know what dV dt is, we're going to have to take the derivative of our volume formula. Now, this is a related rates problem because what we want is an unknown rate. And what we have back here is another rate. They tell us that the depth of water in the cone H is changing at a constant rate of -0.3 centimeters per hour as the water evaporates. So as a derivative, we would define that as dH dt equals that -0.3, and then that's in centimeters per hour. If we're looking for dV dt, we're going to have to take the derivative of our volume formula. Now I want to show you why this is a little bit different than most of the related rates problems, than all of the related rates problems that we did from out of our book. This particular situation is one where our formula, our relationship between variables, has two variables multiplied together right here. R changes over time. As the water evaporates, if I try to draw a different water level, the radius of this surface of the water is going to be different than when it is a little bit fuller, right? So R is changing, H is changing as the water evaporates. So what we have is we have a derivative that's going to require us to either use the product rule, or what we can do is we can use some of the geometry that we talked about for part A. If I draw the similar triangles that we looked at in part A, this would be 5 across the top of the cone, and this would be 10 down through the middle of the cone. If this is just some arbitrary height of water in the cone, and that's R, what we can go ahead and do is we can develop a relationship between R and H, and we can substitute into this so that it only depends on H. We would like this to only depend on H because we have dH dt to work with back here. We don't have dr dt. Now what we could do is we could do some work to find dr dt, but if we can avoid that, we might as well do so. So what I'm going to do is just some more similar triangle work here. I'm going to take the ratio of top of the big triangle to the left side of the big triangle, and I'm going to set that equal to the corresponding ratio of sides on the small triangle, which would be top over left side. And if we went ahead and tried to solve this equation for H, cross multiplying would give us 5H equals 10R, and then solving for H, we'd divide by 5, and so what we'd get is that H is going to end up being equal to, we'll divide both sides by 5, and we're looking at 2R. And if we think back to part A, I think that's basically what we determined with specific values. What we had right here was a version of the same diagram that I just drew for part B. We knew that this was 5. This height on the small triangle was 5 in part A. And when we solved for R, look, we got half of that. So if we double R, if we do 2 times R, we get what H is. That's basically what this relationship that we just established in part B is saying. If we double whatever the radius of the water is in the cone, we're going to figure out what the height of the water in the cone is. So what I'm going to do is I'm going to actually substitute actually I solved this for the wrong variable. I wanted to solve it for R. Reason why, and I just kind of realized this now, I was about to put 2R in place of H, and that would give me a formula here that depends only on R. I want that formula to depend only on H so that we can make use of this. So I'm going to go ahead and I'm going to solve this formula for R, which is easy enough. I'm just going to have to divide H by 2. So I'm going to get H over 2, or 1/2 H equals R. And now if I substitute this in place of R, I'm going to be looking at my volume formula, which is now only going to depend on h, saying 1/3 pi, and then in place of r, I'm going to put h over 2 or 1/2 h. I'm going to use 1/2 h just because I'm going to simplify this a little bit before taking the derivative, and then times the h. And so if we simplify this a little bit, I'm going to square my 1/2 and I'm going to square my h. Well, if I square my 1/2, I get a 1/4. If I multiply that 1/4 by this 1/3, it becomes a 1/12. And if I also multiply that 1/12 by the pi, what I end up with as my constant here is pi over 12. So pi over 12 is going to be equal to h squared times h, or h cubed, or v is going to be equal to pi over 12 times h cubed. And what we want is we want an equation that contains a dv dt and a dh dt so that we can find this and make use of this. And so if we went ahead and took the derivative of this with respect to t, the derivative of v with respect to t is going to give me dv dt. The pi over 12 is a constant, so I'm just going to copy it into my derivative. The derivative of h cubed, now this is a little bit tricky, it's implicit differentiation. H changes over time. As the water evaporates, the height of the water in the cone is going to be getting smaller. So since h is a function of time, we have to use the chain rule. So we multiply by the 3, we subtract 1 from it, we leave the inner function there, and then we multiply by the derivative of the inner function to finish our derivative. And we want to know what dv dt is, so now it's just a matter of plugging in some specific information and evaluating. So dv dt is going to end up being equal to, let's see, well, I'm going to have a 3 pi over 12 if I multiply these together, and that'll simplify, and we'll take care of that in a second. In place of the h, we know that we want to know dv dt when h is 5, so I can put a 5 there, and I'm going to square that 5 right away, and it's going to become a 25. And then in place of dh dt, we have a number that's going to go in place of it too, and that's going to be -3/10. If we think about this for just a second, this is dimensionless. This is just a series of constants. The 5 was in centimeters that we put here, and then we squared it. So this is in centimeters squared. And then the units of this would be centimeters per hour. So we have centimeters squared times centimeters per hour. The units of dv dt would be in cubic centimeters per hour, which makes sense if you think about it. So let me scroll down here and get some more space to finish this off. If we continue to try to simplify this, let's see, I can reduce this fraction here to 1/4, right? 3 over 12 is going to reduce to 1/4. Any other reduction? Doesn't really seem like there is anything else that we can, oh yeah, there is. This 25 in the numerator and this 10 in the denominator, I can divide that by 5, and that'll become a 5, and I can divide this by 5, and it'll become a 2. So let's see, in my numerator I have a 1, a pi, a 5, and a -3. So I think that'll end up being -15 pi if you multiply those 3 pieces of the numerator together. In the denominator we have a 4 and a 2. Multiplying those together is going to give you an 8. And then we said a minute ago, by analyzing the units, that we were going to end up with cubic centimeters per hour as the dimensions on this. So it's a related rates question. It's a little bit different than a lot of the ones that we did in December, since we had to do some legwork over here with similar triangles to make our relationship between variables depend only on h. We could have done some legwork to figure out what dr dt was as well. So that's another way to really answer this question. And to figure out what dr dt is, you would use this relationship, one of these two relationships between h and r. But either way you do it, as long as you're careful, you should get this for dv dt evaluated at h equals 5.